Part of my exploit development journey is to practice creating exploits for known vulnerabilities. This not only makes my programming skills sharper, but it allows me to understand weakness on different kinds of systems. While I was on vacation, I planned the next vulnerability I will exploit. In this video, we will develop an exploit for CrushFTP, an enterprise-grade FTP server. It has a ton of features that makes it popular among different companies. Throughout this video, we will follow the vulnerability analysis from Attacker KB, which is a project from Rapid7. Before developing the exploit, let's try to look for a vulnerable version. I always go with a Dockerized setup first to speed up the installation process. So let's go to Docker Hub and find an appropriate image. Based from Attacker KB, there are 3 sets of vulnerable versions. First will be legacy installations before version 9. Second is anything before 10.7.1. Last will be apps running on version 11 but must be lower than 11.1.0. In Docker Hub, we can see several images here. The first one is version 11. The second and third are most likely version 10. Let's try the second one. Looking at the overview, we confirm that this is CrushFTP 10. Let's go to the available tags and look for versions below 10.7.1. 10.6.0 seems a good fit. I already prepared a separate virtual machine on my local that will run the image, so let's go there. What you are seeing now is a separate virtual machine. I just connected to it via SSH from my Kali. We'll use a slightly long Docker command to run the image, but don't worry, I'll explain the meaning of the parameters. We will do a port mapping so that we can access the container remotely from this machine. We'll set the remote port to 8443 because later we will run another container with a patched version. That patched version will run on a different port. We will create a Docker volume so that any changes we do will persist even when the container restarts. Our container will be named as CrushFTP Vuln. We will run this in detached mode so it will run in the background. Lastly, we will specify the vulnerable version we saw from Docker Hub a while ago. Let's run this now. During its first boot, it will show you the Crush admin credentials on the logs. Let's go get it. The username is Crush admin, and we received some random password. The next time it starts up, this password will already be hidden, so be sure to save it somewhere. Let's see how the admin interface looks like. If we are exploiting an application, it will be helpful if we have an understanding on how it works. Going into my Kali browser, let's access the CrushFTP admin. I already put the IP of that target VM inside my Kali host file so we can easily reference it as target. And we will access it on port 8443 since that is the port we exposed when we ran the Docker container. Let's use the credentials we got from the Docker logs. After logging in, we will land into some sort of file viewer. But since this is a new installation, there are no FTP users created yet, meaning there are no files to see here. In most applications, the admin page is usually the one being targeted by attackers, so let's go there. It presented more things such as several graphs showing system information. To create a user, we need to go to User Manager tab. Let's try to create a test user. Then set the password. Once created, we can configure the directories the user can access. This is usually where the files are being downloaded or uploaded. We can also set the user permissions on the right pane. For example, if we will allow the user to upload files, we can just tick this box. So that's an overview on how the app looks like and what you can do on the admin interface. Let's now proceed in developing our exploit. The vulnerability analysis says that this is an unauthenticated exploit, meaning we don't need any user credentials. It also says that this is a server-side template injection, so we expect that we will deal with some templating engine in the backend. The outcome of exploiting the templating engine will be arbitrary file read. This means we can read any file the user running the app has access to. If it is running as root, then we can read most of the files in the system. Let's create the base structure of our exploit. This is always my first step because this allows me to have a high overview on the flow of the exploit. Let's import the required modules. Since we are dealing with a web application, we will need request module and argparse so that we can pass command line parameters to our script. Let's initialize the parser and give it a meaningful description. First parameter is the target IP, which should be required, then the target port. This may not be required, but let's give it a default value of 443 since that is the default port of the CrushFTP web page. Let's parse the arguments so that they will be available on the global namespace. This allows us to access their values. Before moving on to the next lines, there are some other parameters that is good to add. Since we will be reading files from the system, it is good to pass the target file name as well. There are cases where we don't want to do actual exploitation, but just to check whether the target is vulnerable or not. So let's add a parameter that will identify if the target is vulnerable. Developing exploits is a trial and error process. Most of the time you need to be able to identify the issue with the help of a different tool. In case of a web exploit like this, it is really helpful to pass our request to a proxy like Burp. So let's add a dictionary of HTTP and HTTPS proxies. The idea here is to exploit server-side template injection to achieve arbitrary file read. In theory, it's only a two-step process, but in reality, we need to do more than that to achieve our goal. So it makes sense to wrap all our exploitation steps inside a class. This can also simplify the flow of the program as we can easily pass the important values between each step. Let's create a class called exploit. Then let's add two methods for now, init and run. Under init method, we need to pass the target IP and port since this is the main value we need for our exploitation. We will put a placeholder for now. Run method will be the entry point of the exploit. This will accept the file we want to read. Same as above, we will also put a placeholder. Then let's add the code that will allow our script to run as a standalone module or a program. Let's instantiate the class by passing the target and port. And finally, we need to call the entry point, which is in the run method. As per the vulnerability analysis, the first step we need to do is to get an anonymous cookie. That is by sending a GET request to /web interface. During this step, we don't need any credentials. The server will send back a cookie in this format. After that, we can use that cookie for our succeeding requests. Let's go back to our init method to initialize the important variables we need to use. We will need the target URL of the application. One thing I noticed from the vulnerability analysis page is that there are several endpoints used. Most of them also contain several parameters. It will be difficult to perform string concatenation every time we use them on our request. To make our life simpler, we will build a URL builder function. Essentially, we need to only feed the path and query parameters to get the full URL. So let's go a few lines above to build this function. First is we need to pass the scheme. Most of the time this is in HTTPS, so we don't need to worry about the value. Next is the net location. This is in the form of hostname and port. Same with scheme. This will remain static throughout the exploitation process. Last two parameters would be the path and queries. These will change depending on what step we are working on. The query parameters will receive the queries in a form of dictionary, which is a nice way of handling them since they are mostly key value pairs. The core part of our function is using URL unparse from URL lib module. This is a handy method for building long-form URLs. Based from definition, it accepts a tuple with 6 items, but there is some nuance here. You might think of just passing a tuple in this form, which is what we normally encounter in Python programs. But if you read carefully, it says it accepts a tuple returned by URL parse method. When we look at the definition of URL parse, it returns a named tuple instead of a regular tuple. In order to create that, we need to use named tuple function from collections module. The type name will be the tuple name. Then we specify here the different field names. After preparing that named tuple, we will assign values in this manner. This is just like any variable declaration in Python. We will leave this too as an empty string as they are not required. What's important are the scheme, net location, path, and queries. Our queries are wrapped inside a Python dictionary, so we need to convert them into its proper form. Lastly, once the URL is built, we will return it to the caller. Let's import the modules and methods we used. Now we are ready to initialize the URL. We need to get the anonymous cookie. Using our URL builder function, we will pass the scheme, net location, and /web interface endpoint. Our net location will be the host name and port we will specify from the command line parameters. Then let's initialize a request session object so we can reuse the cookie on each request. We also need the cookie. We need to use a dedicated method to get this anonymous cookie, so let's start creating it. First, let's trigger our HTTP GET request against the /web interface endpoint. Let's skip SSL verification since we will be seeing a self-signed certificate from the Docker container. We will pass our request through burp proxy. And let's prevent HTTP redirects so that we will be able to get the cookie from the first response. If not, the server will redirect us to another web page which doesn't contain the cookie we are looking for. Next is we need to extract the cookie from the setCookie header. These are separated by spaces, so we will split them using that as a delimiter. The resulting value will be a list. We will get the fourth item and strip the semicolon at the end. We will do one final split to separate the items via the equal sign. And finally, we can get the cookie value as the second item. We now have our anonymous cookie, and we can return this back to the caller. Before moving forward, let's verify first if our logic is correct and we are getting the cookie properly. Under the run method, let's put a print statement. And let's don't forget to pass the file parameter to the run method. Let's open another pane and run the exploit. We won't be able to read any file because our program is not yet complete, but we are required to pass something as a command line parameter, so let's just put any arbitrary file name. Let's fire this up. We received a value. Let's go to burp and confirm this. On the left side, we see the request made by our Python program. Then on the right is the response. Let's confirm if this is the same as what we got from our script. Another thing, if you notice there is a 302 redirect. Remember, we disable following redirections from our request. If we didn't do that, we will be redirected to another page which might not have the cookie we are looking for. So in certain scenarios like this, it's good to disable following redirections if not really needed. Now that we confirm we are getting the correct cookie, let's go ahead and build the logic for reading the file. Under the run method, we will store the output in a variable and let another method to get the actual content. Once we get the output, we will just simply print it. Looks simple, but we need to understand how it is done. The vulnerability we are dealing with is server-side template injection. Templating engines help developers with code reusability. For example, if you need to display a welcome page to a new user, you might have a template that looks like this. Then for every user that is created in the system, a dedicated welcome page for that user will be dynamically generated with the help of the template. In CrushFTP, the vulnerability occurs in this part of the code. Any user with the anonymous cookie can specify any file name he wants. The templating engine is wrapping the variable between these two tags. Once it is specified, the output will be returned back to the caller. As a result, attacker can insert his payload as a query parameter via a POST request. Take note that this should be properly encoded. That is also the reason why we performed URL encoding when passing the query dictionaries to our URL builder function. Finally, the full format of the URL we need to exploit will be like this. And of course, we need to include the anonymous cookie. If you notice, there is another small cookie we need to include in our request. This is just the last 4 characters of the original cookie. We will handle this on our script later. Let's go back to our script. Under the read method, let's get first the data we will be needing for our POST request. First is the small cookie, which is the last 4 characters of the original cookie. We can easily do that in Python by setting -4 as the starting index. Then we need the full query parameters for the request. First is the command, which is zip function. We also need to include the last cookie part. Sorry, I just forgot to mention this a while ago. Then the path, which will include the templated input. We will use an F string for this. Last will be the names parameter. This can be any value, but for the sake of simplicity, we will just follow the one from the vulnerability analysis. Next will be the headers. There is nothing too special about this. We just need to put the anonymous cookie, and we are all set. After preparing all the data we need, we will now construct the full URL. Using our URL builder function, we will pass the scheme, which is HTTPS. Then the net location, which is our target host and port. Next is the path before the query parameters. And then last will be the query parameters, which include the file we want to read. we will create an HTTP request, but we will just reuse the existing session from our class instance. Similar with the previous request, let's disable SSL verification, and let's pass this through burp proxy. This function will need to return the output to the caller. We can easily get that output from the HTTP response. Let's do a quick test. We will run same command to get the password file. Let's try to run again, but this time let's look for the shadow file. Since we were able to get it, this means that the application is running as root. This is one of the reasons why it is not advisable to run a program as root user. Being able to read files from the server gives an attacker several advantages. Aside from getting the shadow file and trying to crack the hashes, he can also try to hijack some configuration files that may contain sensitive data. He can use them to access other resources on the server or pivot to another system in the network. Let's modify the script so that it can perform checks against a target without doing exploitation. In order to do that, we need to set up a patched version of the application alongside with the vulnerable one to verify our checks. We need to understand how the patched version responds compared to the vulnerable one. Going back again to the vulnerability analysis, we should be able to find a Docker image with a higher version than the one listed here. This time, let's try CrushFTP 11. Going back to Docker Hub, we can see that there is version 11.2.3. This is higher than 11.1, so let's try this. Let's go to same virtual machine that is running the vulnerable version. We will run similar command. Only difference is that this time we will change the port and name of the container. Now we have two containers running. Let's go to our main function. We already specified the check mode as a command line parameter, so we will just add a condition here and exit once the test is done. Here we specify a class method that will perform the check, but we still don't have that, so let's create it. For the sake of demonstration, let's create a simple logic for the check. If we receive something that we don't expect from the output, that means the target is patched. Otherwise, it is still vulnerable. Question is, what is that response we are looking for? That is the reason why we ran a patched version to figure that out. We know that our exploit will return the output when ran against a vulnerable version. But let's see what happens when we run it on a patched version. It only returns the selected resources not found. To verify if there are any other characters or unseen messages from the response, let's go to burp. We can see here that it's really the only text returned on the response body, so we can safely conclude that this is the message we are looking in a patched version. Aside from the response body, we can see here that the response code is 404. This can also be used as an added check, which can improve the accuracy of our scanner. Going back to our check condition, we can just simply paste that text. Now let's run this against both targets. Let's try first against the patched version. Then run it for the vulnerable version. We can see here that the logic is working correctly. Of course, you can improve this in many ways, such as considering also the response code, or trying this against different versions to see if there are other responses we need to accommodate. Having this kind of check included in your exploit is very useful in different scenarios. For example, if you want to check the servers of your internal network, you can feed a list of hosts to the script and just run it in the background. Let's do one final improvement on our script. If you notice on the intro of this video, I'm running the script in some sort of shell. That is the interactive mode. Exploits are generally noisy in nature. They can be easily detected by defenders. When running our script, we open separate HTTP connections for each iteration. If you need to look for several files, this can be noisy and you might risk of being detected. Some applications may not respond well or worse, crash if they are being exploited multiple times. So, as an improvement to our script, we can make it use one HTTP connection only. This will make it stealthier and reduce the chance of crashing the application. We will add another argument that will enable interactive mode. This will be an optional Boolean value. After that, the next logic will be very easy. We will put a condition that will detect if the interactive mode flag is passed to the script. Then we will wrap our code inside a try statement, a simple Python trick that can give you that shell-like interfaces to create an infinite loop. For each loop iteration, it will ask the user for an input file name. Then we will pass that to the run method, which we already have. Then once that is completed, it will just return back to the start of loop, which is asking the user for the file name. The loop will only exit once a keyboard interrupt is detected. If interactive mode is not enabled, we will just run the script in normal mode, which is by passing the file name as a command line argument. Let's recap the flow of HTTP connection. Once we instantiate our class, it will initialize a request session. That session will be reused inside this loop. That means we are reusing same TCP socket and HTTP session while running the script. Let's test our changes. It didn't work this time. We are encountering conflicting arguments. Our expectation is that we must be able to run either normal or interactive mode. Let's go back to our parser arguments to analyze. We can see here that the file argument is required. That means whatever argument we specified on the command line, we must always include a file. This doesn't make sense with interactive mode because the file we will read should be specified inside the loop and not as a script argument. Question is, how can we turn this Boolean to false when interactive mode is enabled? I will share another Python trick to you. In parser module, these arguments are just normal Python function arguments underneath. That means we can manipulate them, such as putting values that are not really intended as per normal use case. Instead of using a static value, we can substitute something that can yield a Boolean that changes depending on whether interactive mode is enabled or not. Pause the video and think of any possible ways you can do it. We can replace this with a statement that tells whether -i is present as a command line argument. If -i is not present, this will be true, meaning we will be required to include the file as an argument. Else, this will be false, meaning we are no longer required to specify the file, which make more sense. Now, if we try this again, interactive mode will work now without any issue.